Right, so in terms of limit, we can write P1. So this one in the form of Bernoulli equation, right? Um, then we have the dynamic pressures, the inlet, and then rho Gz inlet, P outlet, half rho V I power of 2 plus rho G Z outlet. Now, previously we look at the pitot static probe, right? Let's say this is a pitot static probe. Right, and then we have the pressure orifice. This is the cross section of the pitot probe. And then we connect this pitot probe with the manometers. And we are measuring fluid at these two locations, right? So we have fluid that travels from this location with a velocity Vi. This one is Vi, and then this one is V outlet, right? Here velocity is 0, right? So V1, because we have closed system here. Let's say initially we have a fluid at this height, the same height, right? And then after we measure, we place this probe inside the fluid flow. Because of the pressure here, it will push the fluid downward, so that this one is raised up. Okay, because the pressure here is much more higher than there. Here, because the fluid is attached to the wall, so as I mentioned before, we have this P here, which is equal to rho G, right? This is the static pressure, and this one pressure here is P total, stagnation pressure. And we can neglect these hydrostatic terms, right? So that these two terms become this one is P naught, right? So this one is P naught. And at this location, when we neglect these two terms, because the sensor is very small, so you can neglect the contribution of potential energy here. So we have P naught is equal to Pi plus the hydrostatic here, the static pressure here, plus the dynamic pressure here as well. So how the fluid can stop? So if you look at the equation, mass flow rate equal to rho Va, right? So this is the equation that we use. So the velocity here is 0 if the fluid rho Va, right? We have initial, final, right? So we have this one is equal to 0, the velocity. The density is same because the fluid is incompressible, right? We have incompressible fluid. So the only way that this velocity becomes zero when the area is so big. So how does that mean? So it means that there is the S coordinate system, right? So this one is S coordinate system. Further from it, so we have the fluid moving like that and it become expanding, right? So we have the cross sectional here is so big, right? A is so large. There is another condition that it's possible that the fluid become very small because the outlet area is so large, right? Another possible way that the velocity here becomes zero, you can see that there is a fluid here. So we have isentropic flow in this location, isentropic process, right? So this area is called implicit flow. Implicit flow, we can use this Bernoulli equation. So this is what it means. So I'm going to give you a quiz for today. Let me close this one. Now this is a quiz. So for the quiz, we are going to look at a simple problem. Now let's say this is a floor, right? And then there is a water tank there. And then this water tank, we have let's say a valve. And then we have a pipe. And we fill this system with water. Oh, right. So we have water here. So we have valve, gate valve. Let's say gate valve, and we close the valve first until the water is raised to certain height. Let's say this water is so large, and then after it reaches certain height, then we open the pipe, the valve. Let's say the tube has 25 millimeter diameter, right? Uh, 25 millimeter diameters, and then let's say we have a pressure manometer here, and we find that the pressure at this location is 500 Pascal. This is the we are using gauge pressure gauge, right? So this one is gauge pressure gauge that measure 500 Pascal. And from the pressure drop, let's say here, let's say we have pressure gauge Pascal, pressure gauge that we use is let's say 1000, let's say, just let's say that one. And we are able to use these two pressure gauge, and we obtain that we estimate that the average velocity here 1 meter per second, right? So velocity at this position is 1 meter per second. Now let's say from this location, let's say this is 3 meters, right? So we have a 3 meter. So you have to first the quiz to know whether what is the nature of fluid flow, right? So what is the nature of fluid flow at the outlet? What is the nature of fluid before it's exposed to the surrounding? Okay, and then of course you have to calculate using the Reynolds number, right? I have only 1 second. And then you have to use this information 3 meters for your quiz, right? So this is the information that you have to use when the fluid reach to the bottom, right? So we have splashed there, we have splashed the water there, right? But we just interested at the position where the velocity here is equal to 0, because it stopped, right? Because when it reached to the floor, it stopped at 1 s coordinate system, right? So it will stop here. So I want to know what is the pressure there. So what is the pressure at the floor? Pressure at the floor. So that will be the quiz for today.